which is dangerous because I didn't start Reflector. That means I didn't start my iPad to make this work. Uh-oh, get off of here. Let's go here. iPad. How's everyone doing?
Well.
Good. Well, good. I think the survey is good. Anyone doing bad? Poorly? Bad?
I'm surprised that I'm still surviving.
Nice.
Whoa.
Just kidding.
Surviving this class or just...
Plus semester.
Oh, is it a tough semester for you? I'm sorry to hear that.
I've never taken 3 stats class in the same semester.
Oh, yeah.
You take like 1 or 2 and then another elective.
Yeah, that's a tough go of it. That is not easy. Well, I'm happy they're here surviving, personally. I think class benefits from all of your inputs, including yours, Mayumi. So it's good. What do you guys remember from last time about IRT? Probe it. Yeah. Logit. Fun times, huh? Let's
So
see.
people use logit and probit interchangeably?
Pretty much.
Okay.
Yeah. The transformation is pretty like to get from one to the other. We often use 1.7 as our number. You know what's really funny is I cannot open OneNote, even though that was what I had already started before class. That's so funny. Yeah. Okay. So yeah, I was like, well, I'm going to use OneNote for all my notes because that's it. You know, the problem. Uh-oh. Maybe it's my my iPad just needs restarted. Let's try that. Because turn it off, turn it back on again, see if it works. If it doesn't work, kick it.
That's what I learned from last.
That's right. That's right. Okay, hang on. Anybody have any thoughts? Anything you want to talk about in your mind?
How long you got?
Roche model.
Discrimination.
Okay, Roche model and discrimination. First of all, I want to point you to Roche.org, which is essentially the L. Ron Hubbard of psychometrics. This is Roche is the L. Ron Hubbard of psychometrics. L. Ron Hubbard, for those of you who don't know, Scientology.
Author turned religious theater.
Religious. It's this interesting religion. Yes, I'll say that. Anybody a Scientologist in here? No.
I don't need the Tom Cruise.
That's right. That's right. That's right. So they're this sect of people who have odd behaviors when it comes to, you know, getting people to join their group or whatever else, and that's sort of the Roche model. I'll get to discrimination as soon as I get my slides up here. For the Roche people, this is the Institute for Objective Measurement, Incorporated, and it's this group that does well. I mean, there's nothing wrong. First of all, there's nothing wrong with Roche. There's nothing wrong with the model, and what it boils down to on many levels is the Roche model to the statistical modeling people is a very restricted model because it doesn't have a lot of parameters. Come on. What it boils down to the Roche people is that it doesn't have a lot of parameters, but it has these properties that are very good about it, or they think are very good about it, that make you have better claims about your measurement. And I'm not sure that that's the case either. So, I mean, like, I don't think they're better claims. It's just what happens. So I'll talk about that shortly. I really want to get OneNote open. There it goes. All right. So let's talk about the Roche. The Roche and the 1PL are often conflated. Typically, what's happening in either model... stick the pen in. Get it synced. Now try it. There we go. Okay. Roche. The Roche model. It's also synonymous. It's a one-parameter logistic-ish model. And I say ish because it's sort of what people do in Roche is sort of conflated with its own software and other things that cause it to be a little not exactly 1PL. So if you say, I'm doing a Roche model, but you do technically the 1PL, they'll be like, dude, not the Roche, right? So here's how it's... So I'm typically going to focus on the 1PL mainly because that's going to sync with the rest of the class. What they typically do in Roche that's different is, you know, in the 1PL, in all of our measurement models, we have to set the scale for the factor. Right? So we set the scale typically by setting the mean of the trait to 0. We fix the variance somehow, right? We either estimate it or we set it to value. In a lot of the Roche model work, they don't set the scale of the factor, they set the scale of the items. So but because the items and the factor are on the same metric, we saw this with the kind of the conjoint scaling maps before. You can do that and it's fine. So there's a little bit of backhand of this, but we're going to focus on the 1PL version of its approximation to what Roche is, because it still holds the same properties of it. And so what this is saying is that if we take, well, the probit of the probability, and actually this should be a logit, but I'm doing everything in probits, that y for a person item equals 1, given a theta for a person, it's going to be equal to, and there's several ways of doing this. We saw in the beginning of class it was theta for a person minus b for an item. And do you remember what b was? Difficulty. Right? The other way of phrasing this is to put a common a parameter out in front. And do you remember what a was called?
Discrimination.
Discrimination. Okay. So the common a parameter, if we were to multiply all this through and put it to a form that makes it look like a CFA model, we would get negative a times b sub I plus a times theta for a person. So that the a is sort of taking the place of the factor loading, right? So often when you see this model set up, what ends up happening is that if we specify theta as a normal distribution with mean of 0, variance of 1, and we estimate this model is equivalent, right? So this model up here is equivalent, sorry, this model right here is equivalent to the model where we don't have the common a parameter. We have negative v sub I plus theta p, and we have theta p is distributed. Now this is the case where it's normal. Oh, back up, back up, back up, normal. And in this case, 0, and it's going to be an estimated variance, and that estimated variance is actually a squared. So for the whole, because a is common across all items.
The case of Roche model.
That's right. That's right. So this model, where you estimate a variance, typically we call that sigma squared, is equivalent to the model where you don't estimate a variance, you set it to 1, and you estimate a common discrimination parameter. And the reason for that, if you will, is because if theta has a variance of 1, what is the variance of a times theta? A squared. Its standard deviation is a. Variance is a squared. So think of it this way: if you have a distribution of data x with a variance sigma squared, and then you take, if we add 10 to x, it doesn't change the variance; it's still sigma squared. But if we multiply x by 2, the standard deviation changes by 2, but the variance goes up by 2 squared, or 4, right? And so that's what's happening here, right? So that's the combination for it. They're equivalent models. Yes.
Because I just want to confirm that I understand it correctly.
Mm-hmm.
The Roche model, when the Roche model assumed that there is equal discrimination across the items.
Yes, that's correct.
And in this sense, it's assumed that the items will differentiate between low and high ability of that.
That is exactly right.
So
yes.
This is the main assumption of the Roche.
That is exactly right. Yes. The main way of doing things. Let me just push play here. So what the Roche model is giving us is something that looks like this. These, on the left-hand side, we have the probability that an item is equal to 1 given a person's theta. I'm sorry, that's the y-axis. On the x-axis, we have the actual theta value. Remember, theta and a factor are synonymous.
So we can say paralleleness in terms of item discrimination, in terms of discrimination.
That's right. These lines are parallel for the most part. That's right. Yeah, it's like the same line. The only thing that moves is the location of where the line crosses the 50% mark. Remember, the difficulty is the value at which the theta value, which gives you a 50-50 shot of doing it. It's also the point of inflection. If we did calculus to this, we'd say that this is where the curve, this S-shaped curve, stops increasing and starts decreasing, right? So that's what we call a point of inflection. Jihan, did that answer your question about discrimination? Okay. So the A parameter, the discrimination, because it's constant here, these curves never cross. And that's the part that Roche people love. There's something called specific objectivity, which means, well, hold on to that for a moment. Sorry, you want to say?
You force the data to fit like.
That's right. That's right. Roche people believe data should be this way. And I'll tell you why when we understand the 2PL. When we allow the curves, we're going to see curves crossing in just a bit. So we'll come back to that then. But let's talk a little bit about the A parameter. Remember that A represents the slope of a line that's tangent to our curve here at that point in inflection, the difficulty, right? So difficulty is sort of where that slope happens to be. Now, remember, if you've seen, how many of you have had calculus? Okay, that was me. You should see my high school transcript. I failed pre-calculus. I got a D. No, I failed algebra 2. I got a D in pre-calculus. Yeah. But, so there's a calculus thing that we talk about, though, which is the idea that if we had a given point on a curve, there is a straight line that's called tangent to it, which is essentially just touches that curve at an infinitesimally small value. And that line itself is just straight, right? The slope of that line comes from what we call a derivative in calculus. And we use that for all sorts of things, but this is where the discrimination comes from. If we can imagine a line here versus a line that's right here, right? A straight line that's tangent to the curve, you see this slope is higher than this slope, right? Well, this slope right here, the slope of the line that's tangent to the curve at the discrimination, is the definition of what the discrimination value is. Pardon me, I said that wrong. The slope of the line tangent to the curve at the item difficulty. Like if you were to figure out the slope of the line that's tangent, you've got this curve, there's a line that hits it. What's the slope of that? That slope at item difficulty is our discrimination parameter. So it's a slope, right? And so when we talk about A being very large, the higher A is, the more that line is steep, right? It's a big A parameter. This is a small A parameter because the slope of the line is just changing for each, right?
So you're saying the slope at the point of inflection gives us the
discrimination. That's right. That's right. So when you think about this, it's, yeah.
So what I'm trying to understand is that the length of the tangent line is
infinite. The tangent line itself just is this idea. It's an abstract construct, but we use it for so many things. I have a little representation of a line here, but if you imagine that line going straight off into infinity, into space that way, and straight off into infinity that way, but it's linear. It never changes in its shape. Then that slope characterizes that across all of the universe. That's what we're sort of saying here. I can only draw a little bit without it doing other things.
What we care is the point where it touches.
That's right. That's right. So that's sort of what this is coming up to. That's what discrimination means. So discrimination is a slope. The A parameter is a slope. But if you're talking about the probability curve, which I cannot shrink now. Come on, shrink down. There we go. If you're talking about this S-shaped curve right here, then that slope is with respect to where the difficulty value is. It's the line that's tangent right at difficulty. The slope of the line that's tangent. Now, that being said, if this wasn't a probability, if these were just the actual probits themselves, right? If this graph was, here's theta and here's the probit, right? This is the term that goes into it's like your z-score of that probability, right? Then these lines would look all like this. They'd be straight lines. They'd be parallel. And what you would find is that the slope is the slope of all the A parameter is the slope of all these lines. It's just when we back out and turn it into probability, that slope only applies right at the difficulty value. Does that make sense a little bit?
Yes, but just to the shape of the like the discrimination might be steepest along across the lines, or this will depend on
the discrimination parameter, that is the steepest part right there.
I mean, like,
sorry.
When there is like the steepest this shape.
Oh, the steepest part of the S shape.
So this will change with different data sets.
That's right. That's right. Yeah, that's right. The actual shape of these lines depends on your data,
Okay.
and some have very flat and some have very steep.
So another question: what about the tangent line with the steepest discrimination? Is it line on the?
Yeah, don't worry about the tangent line. Just think of just think discrimination, right? Because the tangent line is just like if you're looking at this S-shaped curve and you're like A is a slope, because that's what people call it. I mean, we talk about a factor loading as being a slope, right? The A is a factor loading. It's synonymous with slope. It's only a slope at that one point, difficulty. That's it. Don't think any more than that, because then we start getting into math that we don't need to talk about here for it. So, no, it's okay. No. Just trying to say, like, there are other parts, and Jesse, you just went through calculus. Help me out here.
Sure.
There are no other lines on here that have a steeper slope than that, right?
It shouldn't be.
That's
Not
right.
in this range.
Because that's what the characteristic of the point of inflection should be, right? So, yes, that is the point. The steepest slope is at the difficulty. So, there may be other of you that have just recently taken calculus, but
Because everything's getting steeper and steeper and steeper right until that point.
that's right. And then it changes and it stops being as steep and it starts getting flatter and flatter. So, but yeah, that's a little too technical. We don't need to worry about that. The main thing we're going to worry about is in the 1PL, the terms never cross, and that's why we have things such as the Koltov-Roche, which give us, where'd it go? Oh, I didn't pull it up here. Roche.org gives us that. And I say all this, but the Roche.org people, one of the people that they love the most is my co-editor at JEM, George Engelhardt. And so he pokes fun at me saying that what I do isn't measurement. And I never poke fun at him, but I sort of talk about him badly behind his back. And so I say, yeah, but my model fits the data better. So the Roche people, let's talk about the 2PL, then come back to specific objectivity. The 2-parameter logistic model is where every item gets its own discrimination, right? So instead of having each item being one way or the other, so this form right here is the same we look at it in a probit or every otherwise. If we were to multiply that through, again, we'd have negative A sub I times B sub I plus theta S, right? That is AI. Dang it. Yes, AI theta S. Yeah. So this is really functioning like your typical CFA model, where there's 2 parameters for every item that measures one factor, right? It's effectively a factor loading. In fact, in item response theory, remember there's these different fields. IRT calls that the discrimination parameter. Item factor analysis calls that your factor loading. It's the same. But when you get that, again, the A parameter still describes the slope of the probability curve at the line that's tangent at difficulty. Right? So it's still there, but let me go to these curves. Here's your curves right here. These curves can cross with different A parameters. And the crossing of the curves, the thing that I would characterize the people in the Roche camp, the Roche commune, trying to think of another way of kibbutz. The Roche kibbutz? No, that's probably that's probably putting down kibbutzes. Yes, the Roche compound, over there in Los Angeles or wherever else.
The deserts of Nevada.
That's right. It's only Nevada, not Utah.
No, nothing weird happens in Utah.
Not at all.
Why would you even say that?
Right there, take a look here. This is let's imagine we have a person who has a theta of -1. Which item below -1, if you have these two items here, the two blue lines here, these two items, by the way, the two blue items, both have a difficulty at -1, right? So that's a 50-50 shot of this person answering the item correctly. Which item is easier for that person below negative? Right, but before, which item is easier for a person with a theta below -1? The way you calculate easier item is the one with the higher probability. So it would be the dark blue line, right?
So which is one.
Right. So it's easier for people who have low ability, but it's harder for people who have a high ability.
Overthink about it.
That's right. Well, who knows? And then you take a look at the light blue line. It's harder for people who have a low ability, but it's easier for people who have a high ability. And that is what drives the Roche people nuts. They should say a hard item is a hard item regardless. Right? So I think there are some philosophical issues with it, right? I mean, what is interesting about -1 for a theta, where some items are easier if you're bigger than -1, but they're harder when you're less than -1, right?
But maybe this is because I have some, like, maybe this is associated with the third parameter.
Yeah, there may be other parameters, right? There may the Roche people will say this is just an item that doesn't fit the world. This is not a good item, so we're going to throw it out.
Would they ever find out that it's a bad item?
Yeah, they have. Well, they try to. They do try to. They do try to. They have statistics in the Roche world. The model fit statistics don't look anything like the rest of the world. They use something. The main program they use is a program called WinSteps. Although there are other versions of programs out there. Anyone ever heard of WinSteps? And WinSteps uses joint maximum likelihood, which was like, we don't want to do that ever again.
What?
Right? And yeah, it's not a good idea. Joint maximum likelihood does not guarantee your results are asymptotically consistent. What does that mean? That means the bigger sample size you get, the more the asymptotic consistency means they converge in probability to their true value. You're not guaranteed to do that in a joint maximum likelihood estimator. So it's an odd thing. WinSteps also, though, provides these fit measures called in-fit and out-fit. And there are certain versions of how well items discriminate with people, and or how well that maps onto what people should do and so forth. I don't exactly know because I haven't studied them. But all I know is that
Not what they actually do.
right.
So this is the reason that they use the Bayesian version.
Well, they don't use Bayes. No, it's
The others like use the Bayesian to make the conversion because it goes for infinity for some items.
no. I don't think that's the reason for Bayes. It's just the Roche people came along and they just really believe in specific objectivity. It means that you're
They have some criteria in mind.
That's right. That's right. And they want to make sure that the model fits the data for everybody and so forth. So yeah. So Roche model, I'm mentioning it because it shows up. But here's the way I look at it. If you look at it from a CFA perspective, it's like basically saying, I'm only going to believe the parallel items model. Right? That's a little weird. So what did we do in CFA? We said, well, we don't have to believe that. We can believe a more complicated model and still get measurement and still get our trait and everything else. And we can test. And if the parallel item model fits better, then that's great. We'll use it. If not, we'll use the more complicated model. And that's the way I believe it. That's the way I teach it. And I don't want to engage in it. If anybody's a dyed-in-the-wool Rashi in here, just plug your ears and send me nasty emails or something. Those of you who, I don't know if anybody listens on YouTube, but our class and my mom. And sorry, and my mom isn't a Roche modeler, that's for sure. But she's Bayesian. No, just kidding. Anyway, you know what I'm saying. So I'm going to stay with the idea. I want to keep on. Really, we're not doing, even though this looks way different than CFA, we're not doing anything different than CFA in large quantities, right? We're trying to apply a model to categorical data and get theta out of it instead of F, right? It's the same idea. It's going to have a scale. We can give people a number from it. You can pay $300 and get your GRE score or whatever else. And, you know. So Yes, this is what this is saying. Items, if you know your construct, items should not vary in discrimination is what they say. But yeah, I don't know about that. So let's see. Let me break this off and go talk about.
So if I'm understanding from the Roche thing, is like there is this one truth. There is this truth about this one construct, and this truth stays consistent.
That's right.
Regardless of population, regardless of data set.
That's right.
And so if there's anomalies, it's because the data set and the people are wrong. They failed to measure this.
That's exactly it. Uh-huh.
And see your earlier comparisons now.
Yeah, right. And so in the same thing, if you think of the parallel items model, we use that to. That's where we developed coefficient alpha from, where all items contributed equally. There's another parallel I didn't mention here. So in the Roche model, when you fit that to data, you have this idea that there's this infinite scale people are on. But the number of scores that you get out, okay, so let me back up. I'll say the statistical term. The total score, like if you add up all the item responses, zeros and ones, is what we call a sufficient statistic for the trait, for theta, which means it contains all the information about theta that we need, which means we can throw away all the rest of the data. We could just take the total score, and it's effectively theta. It effectively correlates with theta.
So you're handpicking your data.
Well, no, you're using a sum score. The Roche model is effectively a sum score. Theta is on a metric that is, you're supposed to think that those scores are different. You know, you can quantify the distance between them. This interval scale, which really doesn't exist because there's measurement error, whereas the total score is on something, you know, much more constrained. So yes, the total score is sort of synonymous with the factor score in the Roche model. But the other thing that means, let's imagine you have a 5-item test. And you have all these beautiful things. You think Roche fits and everything else, and it does, right? Everything's beautiful. How many total scores? I mean, you fit, you know, thousands of people to your data, and you do a histogram of their thetas. You want to see what the distribution of them are. How many scores do you think you have? You have 6. If it's a 5-item test, they're all binary, you get 6. You get the lowest level 0, everybody answers it wrong, and then whatever the sum would be after that. Right? And so it's effectively the total score. The value of theta represents how much more ability or less ability someone's thought to have, or more of the trait or less the trait. But again, the parallel, it's like classical test theory, where people believe classical test theory is one true, like you said, well, the one true thing of the world, right? The only thing that you should believe in. So.
And assuming the classical test theory assumes that all the items
contribute equally, and that's what Roche is saying as well. Mm-hmm. So it's an interesting world. I'd like to go, though, and take a break from the slides and take a look at the example I built to talk about how to do this, because we talked about the 2 models and what they comes out. Let's make this work. This is example 5 on the website, and I actually created a PDF of it for me to draw on rather than to have to click around from before. I don't think you'll find this PDF. But this is an example built off of the a 7-item assessment that has something called the instrumental activities of daily living. And these are 7 items where this is effectively asking people needs help or does not need, asks if a person, older adult, needs help or does not need help in each of these tasks. Right, so think of this as a sample of people who are 80 years and older, and talking about whether or not they do they need help with housework. 64% do, 84% need help with bed making. You know, using the telephone, 94% do. Again, this is an older cohort. I don't know when these data were from, but you can guarantee that when we get older, we won't even have a phone. We'll just talk to it and be like, you know, call my grandson. Right? So it'd probably work a little bit easier. Yeah, that's exactly a nope, no, don't say it. So one of the things I was started to do, because there's a lot of IRT that you don't see when we just use Livan. So I used a package in R slightly at the beginning of these slides called MERT. This is the where'd it go? Right here. This package right here, MERT. MERT's a great IRT package, but as I mentioned before, it has very limited ability to do what we want to do in SEM, which is not have to output the trait and then do a secondary analysis, right? So It does a little bit of that, what it calls a latent regression, but it's not big enough for me to run a class on. But I did a few things in here because there are some parts that we don't get from Livan that it gives us that I'm going to come back to. So I'm going to skip ahead down to Livan, and I'm going to talk about how we would actually do this in Livan. And then we'll come back to see some of the other plots. The other thing that MERT gives us is the ability to plot a little bit easier. I've written some really hokey functions that you probably remember how bad my functions were for homework this time. I wrote a couple functions to do some plots for us in Livan. I just didn't spend the time to build all of the plots that we would get from IRT that we're going to talk about shortly. So I'm just going to show you how to do this in Livan, but realize there's more to it that can be done. Right? And if you're doing SEM where you're not outputting the score, none of the other stuff matters as much. If your goal is to say, I want to say there's a group difference in theta, or my trait, then you won't want to output theta and look at what we're doing. If your goal is measurement, yes, you will want to go in more deeply into it. Okay. So estimation in Livan, what we use to estimate Livan is also not the best in the world, but something called least squares, or in this case, M plus has something they call weighted least squares mean invariance transformation, or WLSMV. So that's what Livan uses. And wouldn't you know, almost all of the syntax in Livan is identical for doing IRT as it is for doing CFA. Yes, right? So you're not having to learn a tremendous amount of new things. This is a section of syntax here that's brand new. My first bit of information on the page is I sort of put all the syntax that you'll see into one spot. To run this model, all you need is, again, just like the bare bones CFA syntax, you need something saying my factor is defined by, right, equal tilde, and the items that defined it. You need that first line. The rest of it you don't need in your syntax to run. But I put it there because sometimes we may want to do stuff with it. Now, in Livan, the big difference between Livan for IRT and Livan for CFA is that in the CFA model we had y for a person and item is equal to mu I plus lambda I factor person plus error for the item and person, right? Or person I. And for IRT, it's the probit of y, and it's going to be equal to tau, negative tau plus lambda I fp. Right? So what's different, the first difference that you're going to see is the intercept is no longer an intercept. It is what's called a threshold. A threshold is like an intercept. It's almost identical to an intercept. But it's not exactly in the right direction, right? So what is a threshold? Let's take a look at this. So every item is going to get a threshold, just like every item gets an intercept. And for an item that has two categories, so in our case, all of the items have two categories, there's one threshold. The number of thresholds, total number of thresholds, for any item equals the number of categories minus 1. All right, so if you have an item that has, it's a 5-point Likert scale and you're going to do the IRT version of it, there'll be 4 thresholds. The way you access those into Livan is by putting the item value, the word of the item, sorry, the name of the item, right? So these are all DIA 1 through 7. So DIA 1, you put the pipe character and you put T1. T1 represents the first threshold. If you know that your item should have 4 thresholds, the way you'd get to threshold 2 would be the name of the item, pipe, T2. Yeah, Michael.
I have a question about syntax.
Yeah.
So inserting the pipe character in, short of just copying and pasting what you provide to it.
Right.
What is the key entry that we would use to do that?
Well, it's the one that's up and down. On my,
It's like a shift function.
it's a shift function. Let me see if I can pull up an example on my. Yeah, the shift and backslash, I think it is.
Ah.
Is that what it is?
Yeah, let me pull my keyboard up and yeah,
Good question.
Come on.
yeah, that is, it's great. I'm glad
I
that,
remember it from multivariate. And I was like,
yes,
oh,
what
I
is,
guess it's a copy of that.
what is that? All right, so it looks like this one, the straight up and down character
Gotcha.
right here.
Okay.
Okay?
Yeah, thank you.
You're welcome. Thank you for asking that. It is a great question. It's one of those things that when you're teaching it, you're like, yeah, I learned that, so far ago, I forgot what it's like when I first got it because you use it all the time. But that's exactly it. And that's the problem I found in me getting older. I mean, there's a lot of problems with me getting older. And maybe if those of you or GTAs, when you're in grad school being a GTA and you're teaching material that you're pretty familiar with because you learned it a few years prior, or maybe even 6 or 7 years, you still have that concept of the beginner, right? And I'm really losing that right now. So these are great questions. I'm sorry. It's making me feel just really ineffective, but this is great. Thank you. Thank you for
I hope that as I grow older, growing smarter is one of my biggest problems.
Yeah, I don't know that I'm growing smarter. I just know that I've lost the perspective of me being in that class when I asked that question before, right? So thank you, Michael. I appreciate that. And by the way, and for all of you who think there's a question that you shouldn't ask it, please. This is great.
Just a question.
Yes, yeah.
Our threshold is here is 1.
T1. Every item, because every item is binary, they'll only have one, and
2
then
minus 1.
that's right. Yeah, and it doesn't matter if your item has labels -10 and 10. It's going to order them from lowest to highest, and the threshold is going to be the first one, sort of the difference between -1 and 1. I'm sorry, -10 and 10. So this threshold, though, it functions like an intercept. All right? That's the only way to think about it. That's how we access it, with the exception of what's called measurement invariance, when we want to test whether our scale is the same, means the same thing across different groups of people or different variables. Most of the time, you will never put the thresholds in the syntax. In fact, I had to look up how to do this because most of the time, it's just like the item intercept. We never do much with it.
So invariance testing involves thresholds.
That does, yeah. Invariance testing also involves item intercepts. So,
The Roche people interpret that.
I don't know if they do. I have no idea. So the threshold is effectively 1 minus the difficulty, right? So it's not going to be. So they're going to interpret the threshold just like they do with the difficulty parameter. So they're cool with that. It's the factor loading or the discrimination that they hate. So, Jesse, did I see a question?
Yeah, no.
Come back. Just no problem. Sorry, give me a chance to drink. Doesn't mean an awkward pause. I'm awkward. You know this, right? So I'm just going to just say it, right? So I make every normal social, bless you, normal social interaction just seem weird. Just, you ever get that point where you're like, God, every conversation I have is awkward, and the common denominator in all of them is me. Anyway, this right here, the other part of syntax that's different is when you call the SEM function to tell it you're going to use this model, you need to put an option in that says ordered equals, and then you give the list of variables that are categorical in order. Ordered meaning 0 means less than 1. It's not a continuous thing. Right? So here I have all 7 of my variables. This, the C character in R, the C function, it basically puts concatenate. It takes every one of those things involving in it, all the quotes, and puts it in one long vector. Right? And so that's atomic vector.
Why do we have to order them? I don't understand.
Well, the word ordered, these are ordered categories is what it's saying. There's a differentiation that Livan does not yet estimate, but
so that it matches the one that we put in the syntax in our model syntax.
No. What ordered means is that the variable itself contains data that have categories that are in order, right? As opposed to nominal categories. Right? Likert scales, right? So in a Likert scale, if someone selects a 5, that means you don't. What we're going to treat the data as is we don't know that 5 means 1 unit more than 4. but we know that 5 is more than 4. We don't know how much more, but we know 5 is more than 4. And 4 is more than 3. And that's what that means. That's where ordered comes in.
Okay.
Yeah, right now it looks like the order of the variables, but no, it means each one of these variable names that I put into this function. So if I put the variable name dia1, Livan's going to say, oh, this variable contains ordered categories. And then it figures out how many categories, what their numbers are, and then puts them in order. Right? Yeah, Jesse.
So is our tau symbol our threshold indicator?
Yes, it is tau. Mhm.
So its subscript is I.
Yes, every item gets its own threshold.
Every item has its own threshold, but there's one fewer thresholds than there are the number of items.
The number of categories
Number
in an
of
item. So
categories.
each item will have a set of thresholds, potentially. For binary items, there's only one. When we get to Likert items, or when we get to items with more than 2 categories, there'll be more than one threshold for an item.
So the number of categories -1.
That's right.
And so every item can have more than one threshold.
Yes.
So is the threshold subscript just I, or should it be I?
And then
Something.
category, usually.
Sorry.
The
it's just
general
confusing.
version of it is sort of an I
Okay.
and like threshold. So like, what is the threshold? Like the order, the category for. So yes, there will be another subscript for it. For the binary data, kind of our gateway drug to the rest of IRT.
That makes sense. There's only one. Okay.
Only one, yeah. It's trying to cut down the minimize the desire for you to use drugs recreationally to like deal with the class. Trying to, but no, it's a good.
I wasn't asking to be a jerk.
No. I don't believe anybody's trying to be a jerk.
Yeah, you do.
Well, the guy I went to grad school with, maybe. But that's only after repeated observations over numbers of years. And him trying to take one of my students' ideas. So, don't mess with my students, man. Anyway, let's take a look at output real quick. Yeah, we'll talk about that. We'll talk later, or maybe we won't. I'll just shut up. The output is going to look surprisingly similar to CFA. Oh, actually, check that. I missed. There's one other part that I want you to put in here. A couple other parts. When you call the SAM function, not only do you put ordered, it's good to put estimator equals, and in quotes, WLSMV.
Excuse me. Actually, I'm sorry, but could you? This is application for what? SEM.
That's a function in Livan. We call.
We don't need to build the other syntax. Just put the first the factors
Mhm.
syntax, and that's it.
That's it.
And it will by default.
That's right. Yep. I think it will. It's been a while. There's a CFA function you can call as well. The CFA makes it shorter, right?
Yeah.
So yeah. So SEM you need the whole syntax. CFA you just need the factor. But you can still put in ordered. Estimator equals WLSMV. The other thing I ask you to put in for this class only is parameterization equals theta. Just do it. It'll make life easy. I don't want to go into the minutia of it. In fact, it doesn't. They're effectively equivalent models. There's different ways because we're dealing with We're dealing with stuff that doesn't really exist. There's ways of trying to play around with how we quantify things. So just parameterization equals theta. I'm saying to do that because there's another option there. But what I'm going to tell you about translating from IFA or CFA version of this to the IRT world is much more direct if you use parameterization equals theta. That's all.
You use WLSMV, so you just want limited information.
That's right. Yeah, the only.
Said IFS. So.
That's right. Yeah, the only estimator Livan will give us to do this is limited information. Right now, it does not have the capability of doing full information for this, and so that's a limitation of it. I would prefer doing maximum likelihood, but we're not able to. Actually, I prefer Bayesian, but we're not able to either. So WLSMV is not bad, but it also what the nice thing about using it is it almost fits almost parallel with everything I just said about CFA. Right? In fact, let me show you. Here's the output. At the beginning, we have a section of model fit that talks about minimum function test statistic, degrees of freedom, chi-square. Well, this is the part in CFA that was our chi-square test of model fit against the saturated model. Right? This is the test. And in this limited information setting, the saturated model means the full correlation matrix. I would say covariance matrix, but a correlation matrix is a covariance matrix with a diagonal of 1. What am I talking about here? In limited information, what Livan is doing is taking our data, turning it into a correlation matrix, and in this case it's called polychoric correlations, which I'll talk about later. They're correlations for categorical variables. Tetrachoric is really for binary. And then it does CFA on that correlation matrix. That's the way to think about it, right? So the saturated model in Livan is the full correlate. It's every correlation is unique. Your model is nested within the saturated model, just like we'd see in CFA. And this test effectively tries to test whether or not your model fits as well as the saturated model, just like we saw in CFA. And that's the nice thing about this WLSMV. Further, the model test baseline model. Does anyone remember what that is in CFA? All correlations are equal to 0. That's right. There's no correlations in your. This is testing saturated versus all correlations being 0. So those are your absolute fit tests that we use with hypotheses testing. What about model fit indices? Well, there's the CFI, there's the TLI, there's the RMSEA, there's the standardized root mean squared residual, or if you prefer, SMRMR. Okay. So there's all the stuff that you'd see in CFA. It's all the same reportable. People who report this hardly even note that they're using WLSMV. And in R, it's effectively you're doing the same process. If you want to test two models, you use the ANOVA function. Technically speaking, what happens behind the scenes, it's functioning differently, but you interpret the result the same way. Chi-square significant means that the model that's nested within the bigger model does not fit as well. Right? Chi-square not significant, models fit the same. Right? So that's what all the stuff you learned for CFA, replicated. Which I like. It's going to cut down on our cognitive demands right now a lot. If you want more IRT, come talk to me after class or something like that, or take Billy's, or I'll point you to my website. Then what comes out of Livan is stuff that we're familiar with also. The latent variables part, this is what we would talk about the factor loadings before, right? These are our factor loadings for each item, right? Our estimate and our standardized estimate, right? We've done all that before, but remember the factor loading is sometimes called the item discrimination here. This is the A parameter. The item intercepts are all fit to 0, and that's because they don't exist. The item thresholds show up, though. Here we go. Yes?
Going back to the item discrimination, the standardization. Are we assuming in this model the Roche model?
This is not the Roche model. This is where everyone is different. So it's a 2-parameter model. 2-parameter numeral ogive is what we are, 2-parameter probit. Or we just got the CFA model, right? So every value is allowed to be different. For standardization, remember std.lv is the standardized factor. What does that mean? That's saying what these would be if you had a factor with a mean of 0, variance of 1. And just like in CFA, you remember the scale identification? Right? In this syntax up here, we set the factor mean to 0, we set the factor variance to 1, but we could have done the same thing that we do in CFA, where we take a marker item, right? If we don't estimate, let's say, the factor loading of the first item, but we estimate the variance of the factor. We can do that here too. All right, so if we had done that, but we wanted to see what the standardized factor would look like, that's what this column is. But this column is equal to the estimate because we have a standardized factor. Standardized.all, though, now divides by some other term. I'm not going to tell you about what it is just yet, but it's a scaling factor. We don't have in this model, what we don't have in this model, remember our CFA model, we had error, and with each error had unique variances. All right? In this probit model, there are no unique variances. So that's part of the issue. Does that help?
Yes, actually, what I was thinking about is that because the discrimination will goes up, like the lowest or no discrimination with 0 and
that's right.
Increasing the value with high discrimination will go.
That's right. Yeah, the discrimination can be anything, any real number. Yeah. What I will tell you is in the IRT world, they use a lot of educational testing, and so they want discrimination to be positive. That there's no. So if you take an IRT class, you may be led to believe that discrimination can only be positive, and that's not true. Just like you can have negative factor loadings, you can have negative discrimination. So, the size of the discrimination is related to the variance of the factor.
But what would a negative discrimination mean?
It would mean that the item is negatively related with the factor. So where that usually happens is when you have forgotten to numerically reverse code an item. And so the discrimination is essentially -1 times what it should be.
Should we delete it immediately?
Look into it. The other issue, the other place it can be is methods factors. If you have, other features of the item that you want to control for, sometimes those are negatively related with the items and so forth. Yeah. So it's all an interesting world, but it is the same as a factor loading. So in the other part, so we don't have intercepts, we have thresholds right here. The thresholds, if we wanted to go from threshold to item difficulty, right, we would take the threshold and divide it by the factor loading. That is our item difficulty for an item. And I mention that because the threshold represents -1 times an intercept, effectively, right? So it basically is saying what is the probability that, or what is the probit, what's the z-score, right? So remember, it's negative tau for an item plus lambda times factor, right? So this is equal to the probit, right, or our z-score. I keep calling the probit a z-score, so think of it as z-score. Because ultimately, if we transform that, figuring out the area under the curve to the left of it becomes a probability. The probit is effectively what is the expected probit when the factor equals 0, right? And so -1 times this would be your expected value of probit, or the z-score, for a probability of a 1, right? So this is going to say what's the probability for. So basically, it's what's happening at the mean of the factor. That's what we're getting here. We'll go back to that in just a little bit. The other part that this estimates is something called scales, but we don't need to worry about that. That's a consequence of WLSMV. We'll just kind of ignore it for right now, or forever. But it also gives you R² if you ask nicely. So the 2PL here, let me see if I can go down to, I have my plots. If I go down further, I put a function together right here called cat item plot, where if you take your Livan estimates and you tell it what item you want and how many standard deviations from the plus or minus to the factor, it will plot the probability of the item itself against, sorry, the item, this is the factor down here, this is theta, against the probability of a correct score of 1 for the item itself. So I took item 2, this is what this is, probability of item 2 equals 1. You have our line here. Now item 2, if I go back to it, let's take a look. Item 2 has a threshold of -3.08 And 3.08 and 2.92. Hang on a second here. Item 2. Right? So these are our values for threshold and factor loading for this. So take a look at, if we were to talk about this with respect to the IRT, the discrimination difficulty parameterization, right? If we had A for an item and B for an item, A would be 2.92. And tau, if you take a look, where's the 50-50 point? It's right here, which is a little bit smaller than -1, right? So B is tau for an item over lambda for the item, right? Or negative 3.08 divided by 2.92. And you'll see 3.08 is just slightly bigger than 2.92. So it's going to give us a value, because it's negative, of negative whatever. Now, I also created a function called convert theta to IRT. So it takes your theta parameterization in Livan and just gives you the A and B parameter from IRT right here. So here, the threshold, and actually I shouldn't call this threshold. This is a B. I'm sorry I didn't take that off. But basically right here, this tells us what? What does that negative 1.054 mean if that's our item difficulty for that item? That means someone has to have a theta of negative 1.054 to have a 50% chance to answer the item correctly. Right? And so the question would be, where is negative 1.054 on the theta distribution? Well, the mean of theta is at 0. So that means this is effectively one standard deviation below the mean. That's like thinking this is an easy item. If you think about what the theta distribution being normal, one standard deviation below the mean means we would expect 30 some odd % of people to be less than that. So 60 some odd % of people should be getting the item right. That's what on it for where.
What's interesting is that's still the item discriminating, although it's an easy item.
Mm-hmm. All right, and there, and in practice, what you're going to find is there's sort of a relationship between discrimination and difficulty. Right? You might find items that are way out here on difficulty. Actually, it's the other way around usually. Items that are really low difficulty may not have a high discrimination, but items out here are like right here. But that's mainly because you may not have a lot of people out on the tails. Often.
So what you just said back up to the point that a person with theta of -1.
Right here?
Yes, so the inflection point is there. So 60% of the people.
Yeah, so what we would expect.
So they would have, what I would say is that they would have 50% chance or
lower. That's right.
Right?
That's right. Yeah, my language wasn't really precise.
That's right.
No, that's right. So here, if we drew the normal distribution on theta, these people below that value right here would have less than a 50-50 chance. Okay. Right. And so the bulk of the people in the distribution is going to have higher than a 50% chance, is what I'm saying. That doesn't mean there's going to be exactly that, but the bulk of it will be higher than that.
One question.
Yes,
I
Amy.
got this example. I'm sorry.
No problem.
Technical question. A couple weeks ago, and that did not have that.
Yeah, I fixed it.
And then when I tried to get in the website, it says
I cannot
fancy
find
meeting you here.
Oh no, did I screw up again?
I have the same question.
Okay. Yeah, I believe you. I'll just need to make a note. Sorry. I screwed something up.
It's okay. As long as we have
Yeah, look at that. I'm sorry. I'll post it later today. Okay.
So
Same
guess
for confirmatory factor analysis as well. There's no access for
Okay, hang on a second here.
just side note.
Add add
I don't want to
links to page 4906. There. Okay, sorry. You put it on my to-do list, otherwise I'll forget it. I'm the type of person that if you ask me something here, by the time I get to my office, I'll forget to do it. So
when you draw the the normal distribution.
Yes.
I understand, but you remind me of the assumption, the essence, the RT that assume that the data is normally distributed.
Right.
So we need to keep.
Well, we don't need to worry about it too much. That distribution assumption doesn't seem to have a big impact if it doesn't follow it exactly. So most of the time, it's not really worried about. Now, in practice, I'm not plotting it for you, but you could effectively look for theta scores. One of the things that Livan, what I don't do in this class, what I'm purposefully not doing, is outputting the factor scores like I did in factor analysis, and that's because the way Livan calculates them is not good. It's somewhat actually very unstable for small numbers of items. So, and the same thing with M+. When you do the least squares estimate, the type of factor score it gives you is not the preferred, the gold standard. So I don't do it. We're not going to touch it here. If you wanted them, the MERT function does that. And let's see if I have them up here. I don't think I plot theta. Oh, there it is. Here's my histogram. Here's all my factor scores. This is the distribution of it. And you know, there's a lot of people up at the ceiling up here. Which actually brings an interesting point. You'll see this. There's only a discrete number of categories of theta as well. And I just said in the Roche model, it's 1 plus the number of items you have is the number of thetas you'll get out of it. For the 2PL, or the 2-parameter model, this is not a logit, but this is a probit. The 2-parameter version has, if you have binary items, it's 2 to the number of items you have. It's the number of thetas that are possible. So in our case, with 7 items, we should have 128 thetas possible. Let me think that's right. 2, 4, 8, 16, 32, 64. 128. Counting binary numbers, right? So there are 128 possible thetas that you can get. One for every unique pattern of responses a person can give you. So each unique pattern of responses gives you a different theta. That's what's happening. So it doesn't look like we have a lot, but what's actually happening here is that we may not have a total number of different unique response patterns in our data. The other thing is that there's a lot of thetas that get pooled for some of these categories. But this category at the top, this is the ceiling. Ceiling of the test. So there will be an upper part for these as well. And you'll note this is definitely not a normal distribution. Right? Almost half of a little bit over half of our sample is up here at the top. And so those are likely people who had answered every item with a 1. And so that actually brings up another issue, which is there are, in IRT, the way it works, depending on how you're picking your scores, we'll go on that later, but it's possible to have response patterns for your scores that they don't give you a number. They have no maximum value to it. Yeah. Sorry.
So based on the scale. Oh
Mhm.
no, I'm sorry. This is binary, so
Mhm.
it's not the scale. It's a need or not need sport.
That's right.
So does this just happen to be the popular sample that they
That's right.
use?
Yeah, this might be. I don't know where the data came from, but I know they came from my spouse, and I believe this is a sample that might have some cognitive impairment.
Yeah.
So most of them are going to need a lot of support to do daily living tasks.
So for the person who uses this assessment, binary one,
Mm-hmm.
might make sense.
That's right. That's right. Yeah, for this sample to have that group. But then what we want to talk about is, if we were doing this, each of these tasks aren't equal, right? And so the thing that we're talking about in IRT would be, rather than taking a look at the total score, right, saying someone above, 5 or more is someone who really needs help, what we'd want to do is look at that distribution of the trait itself and say, well, maybe the theta value at 0 is really the cutoff point or something along those lines, because what this factors in is which items the person, which tasks this person needs help with, right? Rather than just 5 or more, right? Which is the same thing we would also talk about from the CFA approach of versus classical test theory of, the sum score versus something weighted to give us a factor score. Thank you for asking that. Yes.
If you go back to the R squared, like the explained
Yes.
variance, it's not.
Yeah, this is squishy. I don't usually talk about it. So let's not go there because it involves this, and all this is sort of make-believe in the first place. So let's just not. Most of the time for IRT, we don't report that. Because ultimately, we don't have a residual variance to report it on.
This is my question. How you going to operationalize that?
Bingo. Right. Yeah. So it's I don't want to go into that because it's very technical and I don't want to overwhelm us. It's already overwhelming to get to here, I feel like, so I don't want to go there. But it does involve this scale parameter. I'll just say that. The other thing I wanted to note, this is in the slides coming up next, but if you look at, well, let me just do a step further. The last model I run on here is the one parameter model. So in the one parameter model, I constrain all the factor loadings to be equal. This is our tau equivalent model that we saw, or tau equivalent model, not parallel items. I kept saying, whatever I said parallel items earlier in this, I should have said tau equivalent. The parallel items model. And again, we can get our model fit information. We get our factor loadings over here. We get all the same information. But if we want to test which model turns out to be the one we prefer, we can do this ANOVA statement, just like we did in CFA. Now, the method is going to be different. Over there, it was Satora-Bentler. Now, this is Satora 2000. But we get a chi-square with a p-value. Now, I'll note the degrees of freedom difference is not an integer. So that this number right over here is not the chi-square. It's this chi-square. So this we'd say chi-square equals 18.013. And if you were talking about degrees of freedom, some people put that in the denominator. It'd be like 5.04. We have a non-integer degree of freedom, which is actually possible, but we never think about it much in most of the basic statistics we do. So it's part of the adjustment that's done to try to make this an accurate test statistic. So what we would say here, because this p-value is small, right? Remember, H0 is the one parameter model is equal in fit to the 2-parameter model, and H1 is the 2-parameter model is preferred to the 1-parameter model. This would tell us we reject our null hypothesis, and the 2-parameter model fits better, which, in my opinion, is almost always the case. Just like in CFA when I told you, I think Shada asked the question, well, should we test to see if it's tau equivalent? And I'm like, no. The only reason you do this if you sent your paper in and you had a Roche person as a reviewer, or you had a Roche person on your committee. You do that to appease the reviewer and be like, yeah, I told you. It doesn't fit. All right. Now, a couple other notes about CFA comparisons. We could also come up with our, if we talk about model fit problems, we can use the residual function to get our residual correlation matrix. But the only type of correlation matrix we get is the raw type, which means the scale of it is not what we just mentioned before. Remember, in normalized residuals, we looked for things with, they're like z-scores, big or low. These are not z-scores. These are correlations, and differences in correlations, effectively. Right? So this one right here looks big, but it's not standardized. It's not normalized. It may or may not be the case. It's sort of hard to tell. But one thing we can also do is come up with modification indices, and I find these to be a little bit better to work with. And these modification indices will tell us, again, what types of parameters we can add. And in the least squares case, we can, this refers to, right here, this refers to residual correlation between values. In the maximum likelihood case, we don't get a chance to put residual correlations in, but least squares we do. So it's very much like CFA as well.
So we are talking about the same thing, like the construct and stuff.
That's right. That's right. That's right. Construct and stuff. All right. Let me foreshadow a little bit. We're almost out of time today, but next week, one thing we're going to talk about is this right here. This is your factor output. This is the standard error of the factor. You'll note in CFA, if everybody had the same, if everybody gave you complete data, everybody had the same value of the standard error of the factor. If you used my function and you got it to work, what I did, we gave you the factor scores with the standard error to it. For all the data that was complete, it should have one number. In IRT, the standard errors vary. All right, and what that means is the people with a score way out here at the ceiling also have the highest standard error, right? And the higher the standard error, the more error, the higher the standard error, the smaller the reliability, right? Where this test seems to be the most accurate are for people who are down around -0.5.
Does this take us to the GRE?
It does almost, but here is it with some of the missing. These people who are off the curve are the ones that had missing items. But if you look at it, we can come up with something called test information, and that's basically going to be the inverse. This is effectively 1 over the standard error squared, right? So it's an inverse plot to what you see before, but this tells you where you're most accurate for your test, and that again is at -0.5 right there in the middle. But here's the note that I like to talk about. So it tells us we're most accurate for measuring people who are at -0.5, but where are the bulk of our people? Nowhere near that. We're not very accurate for them. Well, we don't have. There's part of the reason why we're not very accurate is we haven't found an item that they didn't need help with, a task they didn't need help with, right? So we don't exactly know where their value of theta happens to be, which we know it's high, right? So that's why the standard error is very big for it. And the same thing would happen for people who are very low, who don't need any help for any of the items, who have 0 on all of them. We haven't found a task they did need help with, right? And so that means we don't measure them very well. So the ceiling and the floor of the test are typically where you have the hardest part to measure. And it's often where, depending on your population, where you have a group of most of the people. But reliability for them effectively probably doesn't matter because you wouldn't make any different decision. If they needed help with all 7 of those tasks, you already know your decision, IRT or not. You need to help them, right? They're having difficulty, or better yet, maybe there's a disease or disorder that's implicated in this. Yeah, great.
Would you say that this is kind of a commonality? Because I think the initial scale was like a 0 to 5.
Right.
So if you cut it at the 1, is this kind of a thing that's going to typically happen?
Like
trying to force it into a binary?
It can, yeah. And actually, we're going to take that initial scale and redo it for the next example next week. So let's take, I don't remember what the plot looked like, but yeah, that's part of it. We might be forcing people to look like they need help if they're at all above a 1 or 2.
So it might be kind of like the a priori, like here's the cutoff.
That's right, yeah, yeah.
Help will have to provide a service.
That's right, and actually that brings up a bigger point. Don't do that to your data. There's a paper I have, one of my first papers is in Psych Methods, which in a methods sense is a pretty highly respected journal. You'll read that I did that. But that was because the reviewers insisted. And I was like, I probably shouldn't have, but I was a junior assistant. Like now I probably would fight more to not do it. But I was like, okay, I'll jump through whatever hoop you need. Just publish my paper. So, but yeah, don't. In theory, what you should do is just let the scale be 1 to 5 or 0 to 5 or whatever, and then model it with a more, with more thresholds. That's what's going to end up happening. Yes.
I have a question.
Yes.
2 questions. So now we have, looking at this histogram, we would have a standard error for each band.
That's right.
The second one is about the, I'm not sure if they have a comparison in mind. Classical test theory would have the most information or the most reliable information in the middle.
Classical test theory does not make the same assumptions this does, and it does the CFA idea, saying it has equal information across the entire scale. So I got to stop there. We can talk after class, but everybody else, thank you, and thank you, Yaya, too. But let's talk about that comment after class because it really gets into classical test theory not really fitting data. So.